Okay, so here we're gonna see if we can follow the numbers themselves. So we know after this it went back to perfectly ordered. 0 always stayed at 0, so 0 went 0, 0, 0, 0. 1 went 1, 2.
Did you go to 4?
Oh, sorry. I'm thinking of those dashes going down and thinking that they were 1s. Sorry about that. And then I was confused because they were all 1s. 1 went to 2. Then to
Oh, the places.
4. Yeah, it went to the 4th place, and then it went to the 1's first place. 2 went to the 4th place, then to the 1st place.
And then to the second.
Second place. 3 went to
To the
6.
6th place,
The 5th place.
and then back to the 3rd place.
4 went to where?
1.
1.
Then
2,
2.
and then 4.
Back to 4.
Okay. 5 went to
5 went to 3.
Mhm.
And then
Then 6. And then 5.
Okay, you tell
so
me
6 went to 5, and then went to 3. And then back to 6.
Alright, and 7 just stayed 7.
7.
Okay, so I'm going to see if we can find patterns in these numbers, in these place numbers.
Well, see sort of what they add up to. But I think they would be varied.
Yeah, what we'd like to come up with is a rule that tells us how to go from one step to the next step.
Well, it kind of looks like we're going to be, since the numbers go in this cycle like this, it kind of hints at maybe modular arithmetic.
Okay.
So we could find like the mod, like for this one, like the mod that's being used here,
Oh,
and
okay.
how to get.
Yeah, that's a great idea.
Well,
Because you could say that you're. No, that wouldn't.
That's okay.
It wouldn't
Keep-
really hold.
Keep guessing. What were you going to say?
I was gonna say that you could use mod 5, and then you go +1, +2, +2 each time.
Okay.
But that isn't. That's kind of random.
All right.
That's not really a general rule.
3 to 6 to 5 to 3. Let's see.
Yeah, modular arithmetic is a good idea. So keep looking. What do you notice in some of these patterns initially?
So in all of the 1, 2, 4 type patterns, so 1, 2, and 4, you only have powers of 2.
Okay.
So maybe from 1 you could look at mod 7,
Okay.
and then you could double each time. So you could add 1, go to 2, and then add 2, go to 4, add 4, go to 8, which would go to 1.
Okay.
And
So
then you could cycle.
So what is that doing each time?
So you're multiplying, for this one you're multiplying by 2, and then you're in mod 7.
Okay.
And that would explain why 0 and 7 always stay the same.
Okay. Yeah. So that rule explains this one, and this one. Okay. Good.
So far.
So let's see, so we multiply, so this way it works because it's generally the same as the one is 1.
Okay.
So you multiply by 2 you get to 4, multiply by 4 you get to 8, and then multiply by 2 to get to 8, and multiply by 2 to get to 2.
Okay. So it explains this one.
So this
So which
one,
means it's gonna do this one too.
Okay.
so 3 multiplied by 2 goes to 6, and then that goes to 12, which is 5 mod 7,
Uh-huh.
and then 10 mod 7 is 3.
Okay, so explains this one.
So it's going to explain these two.
Nice.
So it looks like this rule explains all of them.
So what we were doing is multiplying by 2 mod 7,
Yep.
which is really amazing. Where did the 7 come from, do you think?
Well, you
that's-
brought your last card is a 7.
Okay, your last card was numbered 7.
Beat you to have 8 cards.
And what was special? Why do you think it took 3 rounds of this to get back to where we started? Then, if the rule is multiplying by 2 mod 7, why did it take 3 rounds and we were back where we started?
Because multiplying by 2 3 times is multiplying by 8,
It's
and then which is
one.
multiplying by 1 mod 7.
It's multiplying by 1 mod 7. So there's a very strange thing happening here. That shuffle somehow creates multiplication. Isn't that interesting?
Yeah.
But it's going to allow us to actually, without having to do it for 52 cards, to try to figure out how long it would take for a repeat. Okay, so let's see if we can figure that out.
Alright.